Okay, so our polynomial functions or polynomials themselves, we've looked at and we've experienced before. We just haven't defined them formally. So our polynomials are a function, and the function have a specific form. Okay, so there's the form as our function there. So we have an x coefficient, sorry, we have an x term to a power, and as long as that power is a positive integer, it's a polynomial function. So in other words, if we have x squared, well, we'll go x to the 4 plus 3x squared plus 2x plus 1, that's a polynomial because each of the powers are positive numbers, okay? In terms of defining things, the numbers in front of the x are called our coefficients, okay? 0 is, I guess you could argue, 0 is a polynomial because if you think about 0 is the same as 0 times x to the 0. So that's a positive indice or positive number. So it fits my polynomial form. All right. The degree of the polynomial is the highest power of my polynomial. So for example, if I have a polynomial 2x cubed plus 3x plus 4, it's got degree 3. Okay. As opposed to x squared plus 6x plus 1, well, it's got a degree 2. All right. If I have, however, x squared plus x to the minus 2 plus 4, it's not a polynomial because that's a negative number. It's got to be a positive whole number or 0. All right. That 4 on its own, that's the same as what I was saying before, x to the power of 0, because anything to the power of 0 is just 1. All right. So as I mentioned, that 4 there, well, that's my constant term, okay? In other words, the index is 0. So in terms of just doing a little bit of evaluating, well, there's my sort of function notation, isn't it? Typically, we might use p of x. We talk about our functions, often use f of x. Well, often for a polynomial, we'll go p of x, all right? P of 1, we substitute 1 into the rule. So I get 1 to the power of 4 minus 3 times 1 cubed plus 2, which is, well, 1 to the 4 is 1 minus 3 plus 2, which happens to be 0 in this case. P of negative 1, substitute negative 1 in, I get negative 1 to the power of 4 minus 3 times negative 1 cubed plus 2. Negative 1 to the 4 is negative 1 by negative 1 by negative 1, etc. So that's positive 1. Negative 1 cubed is negative 1 times negative 3 is positive 3 plus 2, which happens to be 6. Okay, so it's just evaluating our functions in the same way. P2, notice how whenever I substitute in, I tend to put the term in a bracket. That way we can be really sure to make sure we take into account any negative signs. That's a cubed plus 2. 2 to the 4 is 16 minus 2 cubed is 8. 3 eighths are 24 plus 2. So 16 plus 2 is 18 minus 24 is negative 6. P of minus 2 is equal to negative 2 to the 4 minus 3 times negative 2 cubed plus 2, which again is positive 16. Negative 8 times negative 3 is positive 24 plus 2, which is 42. Okay? So let's just have a look at our next example here. We've got two different polynomials here, one called p of x, one called q of x. Find p of x plus q of x, which is exactly that. This was our test. P of x plus q of x is just, well, let's put that in black. X cubed minus 6x plus 3 plus q of x, x squared minus 3x plus 1. So x cubed, no other x cubes, so that's just equal to x cubed. I've got one lot of x squared there, so it's plus x squared. I've got minus 6x minus 3x, which is minus 9x. What's that? A plus 3 plus 1, which is plus 4. Okay, if I want to subtract them, exactly the same thing. X cubed minus 6x plus 3. Subtract this time. Put it all in a bracket. X squared minus 3x plus 1. Because now we're going to be careful. X cubed, that's the only x cubed term. I've got a minus x squared. Minus 6x minus 3x. So minus of minus 3x is plus 3x. Negative 6x plus 3x is minus 3x. 3 minus 1. So 3 minus 1 is 2. Okay. If I'm going to multiply them, it might be a bit messier, Mr. Gar, it certainly is. So let's go x cubed minus 6x plus 3 times in bracket x squared minus 3x plus 1. So one at a time. X cubed, let's do x cubed times everything. Yeah. So x cubed times x squared, add the indices, 3 plus 2 is 5, is x to the 5. X cubed times negative 3 is minus 3x to the 4. X cubed times 1 is plus x cubed. Let's get the next term now, which is minus 6x. So in red, minus 6x. Minus 6x times x squared is minus 6x cubed. Negative 6x times negative 3x is positive 18x squared. Negative 6x times 1 is minus 6x. We're at another one. 3 now, 3 times everything. I'll come down a little bit, plus 3x squared minus 9x plus 3. So let's put them all in maybe yellow. X to the 5, it's the only x to the 5 term. I've only got one x to the 4 term. Now I've got x cubed minus 6x cubed. So it gives me minus 5x cubed. So I've done that, and that. 18x squared plus 3x squared, 21x squared, minus 6x minus 9x is minus 15x, and I've got plus 3 left. Okay, so a lot of it's just getting used to a little bit of terminology, but that's just applying my index laws. All right, so if we have two polynomial functions, the only way they can be equal, the whole polynomials, is if the x squared terms of the x squared coefficients are the same, the constant coefficients, if every coefficient has to be the same. All right, so for example here, if p of x is equal to 4x cubed plus 5x squared minus x plus 3, well then q of x has to be exactly the same. bx squared plus cx plus d, which means the 4 has to be the a, the b has to be 5, negative 1 has to be c, and the constants have to be the same. Okay, so it's the only way the two polynomials can be the same is if they're identical. All right, so let's have a look at the example. P of x is equal to x cubed plus 3x squared plus 2x plus 1. And that's got to be the same as q of x. So we're at BC, find the values of B, C, and R. Well, really, we've got this expression here. So we're going to have to expand the whole thing and try to get it to look exactly the same. So if I do x times everything, I get x cubed plus bx squared plus cx, now multiplied by negative 2 minus 2x squared minus 2bx minus 2c, and I've got the plus the r left over. So for this to be the same, all the x cubed terms need to be the same, the x squared terms, the x terms, and the constants need to equal. So let's just get our x cubed terms here. There's only one. So I'll do it there. There's my x cubed term. That has to be the same as that one, so that doesn't really help me too much. What about my x squared terms? Pick a different colour. Right? X squared term here is 3, and that's got to equal these x squared terms. Well, there's one of them there. It's b. So if you like, 3x squared has to equal bx squared minus 2x squared. Yeah? So if I solve for that, so now I can sort of ignore the x squareds if you like. I've just got to make sure that the 3 is equal to b minus 2. Therefore, the b value has to be 5. Because what I'm really saying is if I put a 5 in here now, I get 5x squared minus 2x squared, which will give me 3x squared, which is that term. What about the constant term x? The blue one, the constant term is 2x, and that has to equal, where's my constant there, cx, sorry, my x term, minus 2bx. So they have to be the same, which means now let's just look at the x coefficient. The 2 on the left-hand side has to equal c minus 2b. b is equal to 5, so that means then that 2 is equal to c minus 10, so c has to be equal to 12. Let's go to my constant term. What's the constant in the blue polynomial? That's 1. And that has to equal the constant in the other big black one. So there's a constant term and there's a constant term there. What makes them constant? Well, they're not multiplying any x value. Okay, so neither one of them have got an x term with it, so that makes them constant. So negative 2c plus r has to equal 1. So c is equal to 12. So therefore, 1 is equal to negative 2 times 12 plus r. So r has to be equal to 25. So there's each of the values. All right. So there's a couple of things that we've sort of terminologies we've used there. Polynomials, okay. Just a function with x to the power of a positive number. We talk about the coefficients of the terms, which is the number in front of the x or the x squared or the x to the 3, whatever it happens to be. And for them to be equal, each of the values need to be identical. Okay? So there's another example there in the book, but let's get into it.